Hi guys, this is Mrs. Cribb, and we are going to go through the properties of the families in the periodic table. And so I want you to turn to your notes for this section 514. So if you don't have your notes out, pause the video for a moment and get this section up about the hydrogen family. And I'm going to kind of flip back and forth between writing on the notes and watching a few videos that show some of the reactivity of these families. And I also want you to know I will highlight as we go the things that I want you to memorize about these groups, but a lot of this information, I just want you to hear about it and get some feel for the reactivity. And I'll ask you certain questions about them, but I'm not going to expect you to memorize every little minute detail about all of these groups. The first thing to memorize is the hydrogen family, hydrogen H2, a family all by itself, okay? And so that's easy to find on the periodic chart. I'll flip down to the periodic chart in our notes. Here they are. There's hydrogen all by itself. And notice it's in group 1 or 1A. And so that means it has one valence electron. So remember that here's the one proton, and it has one valence electron. And so hydrogen really just needs one more electron to fill its outer shell, because remember the 1s can only have 2 electrons total. Right now it only has the 1s1. So hydrogen hunts that other electron to fill it up, or it can let go of that electron. And when it leaves that electron, we just have that one proton sitting there, and it has a +1 charge now. Everything in column 1 usually gets a +1 charge because they lose one electron, or subtract one negative, you get a +1 charge. So hydrogen is one of those. Let's go back up to the hydrogen family. It's a gas at room temperature, and it has properties of nonmetals, which we've already talked about the properties of nonmetals. It's colorless, odorless, tasteless, diatomic, one of the diatomic. Remember the diatomics: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, or iodine. You need to remember those. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Hydrogen's one of those, so it's H2. And hydrogen can be compressed into a gas as low as -250 degrees Celsius. So that's not compressed into a gas. It can be a gas at that temperature, which is very cold, but it can be compressed into a solid. So I can push all the molecules together to make it a solid as low as -259 degrees Celsius. So that's a little bit weird. It can be a gas at 253, but I'm not pushing the molecules together, -253. And it can be a solid at -259, and I am pushing the molecules together. It reacts with like group 1 because it has that one valence electron, but it also reacts like group 17 because it only needs that one more electron. Remember again, one proton, one electron in the 1s. But if I get one more electron, now it would have 2. It can only, that 1s can only hold 2, so now it would be a 1s2. It would have a complete outer shell. At room temperature, hydrogen is stable, but at high temperatures and pressures, it can easily split apart and combine, sometimes explosively, with other elements. And it combines with many elements to form common but important compounds like ammonia and H3, and many compounds with carbon. Those are called hydrocarbons, and we're not going to get a chance to cover those a lot, but we will touch them a little bit as we move on through the year. It is found in trace amounts in the Earth's atmosphere. Hydrogen can also react with things in group 17 or 7A. So let's look down here, like chlorine. Okay, hydrogen can react with chlorine. That's in group 17 or 7A. And if it does, if hydrogen reacts with chlorine, we get hydrochloric acid, HCl, and it's one of the important strong acids. And we'll learn a lot more about that, though, in chapter 16, at the very end of the year. Okay, ammonia, so space program uses hydrogen for fuel, and ammonia, NH3, is used in crop fertilizer. So we're going to go now to the Prezi, And what I did is, here's the chapter 5 Prezi, but then it has embedded the table, the periodic table Prezi. So here's the periodic table Prezi, and there are videos for each group or for most groups. So we're going to skip over this. These are old notes, but we are going to watch a video here.
Got it.
We've done some really nice experiments with bubbles containing hydrogen gas using our slow motion camera. The experiment was really quite simple. Up here we had a burning spill, just a piece of wood like a large match. And underneath we had a bubble blowing kit, just like this. And we blew hydrogen gas through it. Because hydrogen gas is lighter than air, the bubbles flew up towards the flame. For me, one of the most surprising things was how hard it is to hit a flame with a hydrogen bubble. Most of our bubbles missed, and they floated up reasonably slowly. And you have to remember that a small bubble has a higher pressure of gas inside it than a big bubble. So if you have a big bubble, the pressure is pretty low, almost the same as atmospheric pressure. But what this means is that if you burst the bubble, the gas isn't under pressure and doesn't expand very rapidly. One of the things that I thought was interesting is that when a bubble catches fire, the burning gas continues to move up almost the same shape as the bubble. It expands a little bit, but it continues upwards. And the other point that we saw from these bubbles is that even though the soap has disappeared very quickly, the gas still burns with an orangey flame. I think that's interesting because it shows that the gas is still experiencing a buoyant effect and the rising up. And the fact that it suddenly goes to a very high temperature does not really seem to change the rate at which it goes up. Look, this one's quite fun. It's double, just like a hydrogen molecule. I was expecting that this would burst twice as much as a single bubble, but you see, it's more or less the same. So you can't always predict what's going to happen. So it was quite an anticlimax, but it's quite nice to burn a hydrogen molecule containing.
Okay, so there we were watching hydrogen gas bubbles and showing you how flammable they really are. Okay, let's continue on with our notes. So now we move on to the group 1, the alkali metals. Okay, this is again one of those things I want you to memorize. I guess I should mark them. So memorize the hydrogen family, H2, and where it is. Memorize the fact that it has one valence electron, which you should be able to know because it's in column 1. Memorize the fact that it's a gas, which you should pretty easily know, and that it acts like group 1 and group 17. There's not a whole lot else I'm going to have you memorize. I told you it can be a +1 charge. Well, the group 1 elements can be a +1 charge, so if it loses its electrons, it's 1 electron, it becomes a +1 charge. And most of the group 1 elements, that's what's going to happen under most circumstances. Hydrogen's one of those weirdos. Okay, that's why it's a family all by itself. So it can be a +1 or a -1, but most of the time the group 1 elements will be a +1. We'll go a little bit more into oxidation numbers and what causes them in a later chapter. So now we're in alkyl family, the group 1 elements, and I want you to memorize the name there and where they're located. So this is group 1. We'll look very quickly down here at the periodic table. That's this one right here. So we're talking really about lithium and down to francium. Remember Mama Francine with her 87 babies? Well, this is lithium. They all are going to be a +1 charge because they're all going to lose their valence electron, their 1 valence electron from group 1. So back up to the notes. They are very reactive, and their reactivity is actually going to increase as we go down the chart because it gets easier and easier to remove the electrons. That first ionization energy gets smaller and smaller. So they have one valence electron and it only needs to get rid of that one to have the octet. So they usually have a +1 charge. You need to know these things that I'm putting in red. Sodium is the most abundant. Sodium must be stored in oil, in fact, so it won't react with water. They are gases. We're talking about metals now. They're solid at room temperature. And let me change that color. You don't have to memorize this particular thing. They are solid at room temperature, and they have low densities, and they're very soft, super soft. You can cut them with a knife, okay? Like sodium can be cut with a knife. They're very reactive because of the one valence electron. They react easily with water, and none are naturally found in their pure metallic form. Now the reactivity, which I told you they're very reactive, I want you to remember this, that the reactivity increases as you go down the chart. Because as you go down the chart, they're going to get bigger and bigger and bigger and bigger because they're adding more energy levels. And that means their ionization energy is going to go down. So it gets easier and easier and easier to take away their electrons. So let's go to the periodic table Prezi. We're going to move on to alkali metals. So there's alkali metals, and let's watch this video for a few minutes.
Alkali metals are soft, silvery white metals that are good conductors of heat and electricity. Lithium, potassium, and sodium are very reactive with water and do not exist free in nature. Alkali means basic, and many sodium compounds are effective at neutralizing acids. For example, sodium hydrogen carbonate can be used to relieve acid indigestion. The strong base sodium hydroxide effectively dissolves fats, grease, and hair in drains. Alkaline earth metals are harder and more dense than the alkali metals. Although magnesium does not react with water, calcium...
Okay, so here he's talking about the alkaline earth metals, which are the group 2 metals. So we're going to talk about them in just a second, but go ahead and watch this video about their reactivity.
And barium do. Because of their reactivity, these elements do not exist free in nature. Calcium hydroxide, known as slaked lime, is used in farming and gardening to neutralize acidic soil. Dissolved calcium and magnesium compounds are commonly the cause of hard water. Insoluble barium sulfate is used to provide contrast during X-raying of the intestinal tract.
Okay, and then here's one more about the reactivity. I mean, that's a really good one about reactivity.
Whether you've left school or you're still at school, you can appreciate the sheer fun and mayhem that chemistry can be. There's so much to it. Bunsen burners, mixing chemicals. Very nice. Now, you may have been allowed to mix very small amounts of lithium with water. You may, if with a responsible adult, have mixed H2O with sodium.
Oops, sorry. Let me go back to that. All right, I wanted to look at the notes real fast because he's now talking about the reactivity of these alkali metals. And so he had talked about lithium, like he said you may have been able to mix lithium with water. So he did this one, and sodium, but he's going to work his way down with potassium, rubidium, and cesium. And notice how we're going down the chart, so we're getting bigger and bigger and bigger and bigger and bigger. And easier to take away those electrons. Okay, so let's go back to the video. I did it again, hold on.
Strict scientific control have witnessed potassium mixed with water. But the odds are, if you have, it will only ever have been on one of those rubbish science videos. There you go, mate, present. Oh, thank you very much. These next two are the dog's nuts of the periodic table. They are, if you like, the king and queen of alkali metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so...
Okay, so notice that, okay, they have that shiny metal in the tube, and that's rubidium, and it's in a glass tube, that special kind of tube that's going to dissolve in the water once they put it in, so that then the rubidium will hit it, okay?
What's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
Okay.
Good luck. Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody. This one's going to be bad.
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone.
See, that's pretty reactive, and that's rubidium. You haven't gotten to cesium or francium.
Yes!
Wow.
That is more like it. Only on Brainiac do you get that kind of science. But I believe we can go one better. There is one more alkali metal we can legally use.
Yes, Richard, cesium, the emperor of alkali metals, particularly nasty, could go off at any time.
And that's it.
Oh, yes.
Brilliant. I like it already. Now, what's that going to do when it hits the water?
Imagine a depth charge in a bathtub.
Fair enough, mate. I'll leave you to it. Good luck.
Thank you.
Okay, John. Go for it.
Warning, 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 extreme danger, clear the area.
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion.
Alright.
And it does.
Alright, so now, they actually cannot use francium for this kind of thing because it's difficult to get and difficult to collect and also very dangerous. So let's move on to our notes. So we've just now covered alkali earth metals. No, alkali metals. Now we're on alkali earth metals. Okay, so what do you need to know? Group 2 are the alkali earth metals. You need to memorize that. They have a +2 charge because they lose 2 valence electrons. Remember, subtract 2 negatives because each electron is a -1, and you get a +2. So we have 2 valence electrons, so the charge is a +2. They're very reactive. They are denser and harder. And actually, you don't have to remember that part, so let's put it in green. Harder and have higher melting points than alkali metals. And that has to do, that word is harder, it has to do with how it's constructed, how small the atom is. Remember, the alkali earth metals will be slightly smaller than the alkali metals because they're being held a little bit more tightly. Okay, you don't have to remember this, but beryllium is one of those, and it's in emeralds. Calcium is the 5th most abundant substance in the earth. The physical properties, they're silvery to white in appearance, slightly higher densities than alkali metals. It says right here they're denser, and they're all malleable. Remember, one of the properties of metals is that they're malleable. Okay, and they are actually much harder than group 1. It does say they're harder up here, but they're a good bit harder than group 1 metals. Chemical properties, the elements at the bottom are the most reactive because the electrons are the most loosely held, and they have many uses. Beryllium's in X-ray tubes, and they showed you that. I think they showed you beryllium being used in that other video. Magnesium is often used to make lightweight alloys for airplanes and automobiles and boats, and it's also used for military flares because magnesium burns with an intense light. Okay, so let's go back to the videos. Okay, here's this one. It's not quite as fun as the other one. It's just showing you a few facts about it. So we're not really going to watch a whole lot about that one. So let's just move on. Back to our notes, actually. All right, sorry for the jumping around. Let's see. Now we go into the transition metals. And when I did these notes, I didn't realize they were kind of cattywampus here, but you need to know that the transition metals are in the groups 3 through 12 on the periodic table. So let's look again down here. This is group 3, okay? So this is group 3, and there's group 12. So it's the D block, okay? The D block elements are the transition metals. And let's talk about some of their properties. Go back up to the notes. Transition metals. Most commonly, these are the most commonly used metals, like copper and iron. And there'll be a few more in that group that you're going to learn. Precious metals like silver, which is Ag, and gold, which is Au, and platinum. And physical properties, typical metal properties, they're shiny, they're malleable, they're ductile, they conduct electricity and heat. Some are magnetic, and all except mercury are solids at room temperature. So you do need to know that mercury is a liquid at room temperature. So these things in red are things you're going to have to know. Notice the sign, the symbols for the different elements, and the fact that mercury is a liquid. Okay, chemical properties, some like gold, silver, platinum resist corrosion. So I'm not really going to ask you to memorize that. Others corrode quickly when exposed to air, like iron and copper. So that brings us to the inner transition metals. And this is something else you need to memorize, where the inner transition metals are. And that's the lanthanide and actinide series. They are F block, and they are paramagnetic, which means they have a weak magnetic field. We're not going to go into a lot of the details, but let's go down here and find them. So here's the D block. Those are the transition metals. Here we go. There's a big circle. That's the F block, and they are the inner transition metals. Okay, now we could put them all right in here in these spots, and I've already showed you a periodic chart that could be expanded. So that's where those show up. So the D block are the transition metals, and the F block are the inner transition metals. Okay, let's go back up to our notes. So now we're going to talk about the post-transition metals, which are 13 to 16. So these are things you need to memorize. And we have the metalloids, and they are semiconductors. Metalloids are semiconductors, and that's in an earlier part, so you do need to know that. They conduct electricity under certain conditions. So this group 13 is a boron family. Okay, you're going to need to know that. Now that's easy. The names of these families: carbon family 14, group 15, the nitrogen family. These are easy things to know. So let's go down and look at groups 13, 14, 15, and 16. Let's go ahead and get to 16. All those are things you need to know, but they're super easy because all they are the name of the first element at the top. So there's group 13, and it's the boron, the first element family. Group 14 is the carbon, the first element family. Group 15 is nitrogen family. Group 16 is the oxygen family. See, nothing hard there. They're just the name of the element at the top of the column. So you need to know alkali metals, alkali earth metals, transition metals, inner transition metals, boron family, carbon family, nitrogen family, oxygen family, and then these next two have special names. Okay, so let's go back up and talk about them just a little bit. Boron family, boron and aluminum are the most important economically. Aluminum is the most common metal in the Earth's crust, and it's found in clays. Carbon family, carbon compounds are the basis for life, and like I said, these are hydrocarbons. Most of them are hydrocarbons made with hydrogen and carbon, and then some other elements. We're going to touch some of them. Some of the lipids and proteins we'll get to see. They're solids at room temperature. So what do you need to know about the carbon family? It has 4 valence electrons. Well, again, that's easy because look back down at the carbon family. It's in group 14 or 4A. So everything in this group have 4 valence electrons. Boron family is in group 13 or 3A. So everything in that group has 3 valence electrons. So that's not anything really new. Group 15, the nitrogen family. 78% of the Earth's atmosphere is nitrogen. White phosphorus is phosphorescent and is the original source for this name. Extremely reactive and will burn spontaneously in the atmosphere, poisonous in small amounts. Nitrogen's largest use is in producing ammonia, NH3. So just like hydrogen is used in ammonia. Oxygen family. Oxygen, colorless, odorless, tasteless gas. 21% of the Earth's atmosphere dissolves in water. forms oxides with other elements, and we will come across oxides like carbon dioxide or carbon monoxide, nitrogen dioxide. So we'll learn about all those oxides when we cover the names in Chapter 8. And sulfur forms sulfides, and so we'll cover those as well in Chapter 8. So really, you just need to know that the oxygen family is group 16, has 6 valence electrons. And what charge, though, do you think that, and this is one I really probably want you to know. Group 16, 6 valence electrons. Well, that means it needs only 2 more electrons, right? Because so here's the nucleus, and it has 6 valence electrons. I'm not drawing all of that. 2, 4, 6, 8. It has only 2 holes. 2 holes to make that complete octet. So if we go grab 2 more electrons and fill up those holes, we have an octet. So when we add 2 negatives, we end up with a -2 charge. So group 16 is normally a -2 charge, and that's something you need to know, okay? Because it adds 2 electrons. It adds 2 negatives. So that is something to know about group 16. Group 15 is often a -3, but it's going to have other oxidation states. So mostly I want you to remember this one, okay? We're not going to worry about this one too much, not yet. We're going to look at all the exceptions soon. Now we get to group 17, the halogens, one of the most famous groups, okay? The halogens. This is group 17. I guess you could call it the fluorine family if you wanted to. It's the most chemically uniform group other than noble gases. It forms salts. So halogens are salt formers, okay? Salt makers. And like metals, like sodium and chlorine makes sodium chloride. It forms salts with reactive metals. Well, what are the reactive metals? That's the either group 1 metals or the group 2. So chlorine is in group 1. And they're generally very reactive because they have 7 valence electrons. So this is, you need to know this. They're very reactive. So these are halogens you need to know a good bit. They're halogens, group 17 or 7A. You can do that easy. That means they have 7 valence electrons. That means they need only 1 electron. So they're going to be a -1 charge. They need only 1 electron. So they have 7 valence electrons, like fluorine. 1, 2, 3, 4, 5, 6, 7 valence electrons. They add 1 more, and that makes it a -1 charge because you're adding 1 negative to make a -1 charge, because every electron is a -1. Okay? So they're -1 charge. They're very reactive. Now, remember how up here we talked about as the sizes got bigger, the reactivity got more reactive, and that was for the group 1 because they got to where they let go of the electron more and more and more. Okay, well, it's the opposite for the halogens because fluorine, they do get bigger as you go down, but that means fluorine down here is tightly holding to all its electrons, and it sucks in electrons faster and faster than the one down here. They're weaker down here. So the reactivity, in this case, the reactivity, it's more reactive at the top, okay? Because rather than giving away electrons, like group 1 is, they're taking in electrons. And so fluorine is tightly holding on. Remember, fluorine is the bully, and it takes the electrons from everybody else. So let's go down and find that on the chart. There's fluorine. There's the halogens. This group right here, the halogens. And I think it's all over here somewhere. I don't notice it being written over there. Okay, halogens. H-A-L-O-G-E-N-S. -1 charge. Okay? Okay, I brought you back over to the videos, and we're first going to watch one about the oxygen family that's just kind of for fun, and then we'll watch the ones about the halogens.
Hey Tristan. Hey, what? Have you ever heard of the oxygen family? Nope. Well, I wrote a song about how they're all so special. Go ahead. attractive, somewhat room temperature gas. Spaceship, corrosive, very explosive, and chemically some part of ash. Sulfur, we use salt dome extractions to make great reactions when burning the stuff on a match. You can grind it up longer to make it burn stronger. Use the welder detach. Selenium, it's rarely found pure and dangerous for sure, sometimes essential in plants. It's used to make glass, rarely a gas, so be careful to keep it off ants. Tellurium in machinable metals, for example, white petals, it's used to make cutting them fast. It was thought to be rare, just escaped through the air, and commercially come last. Polonium, deep in the crust, low below dust, it lies so deep in a ash. It's seen in some ore, but never found pure, a product of when neutrons smash.
So I see they're all different. So how are they the same?
Well, they all have 6 balanced electrons. They are a family after all.
Anything else?
No. No flick production.
All right, that's it of that one. Okay, so let's move on now to the halogens.
Group 7 of the periodic table is a group of non-metallic elements called the halogens. Iodine, bromine, chlorine and fluorine are very reactive, so they're not found as free elements in nature. Fluorine is a gas, but it occurs in a rock called fluorspar as crystals of calcium fluoride. This is chlorine, a poisonous pale yellow gas. The commonest chlorine compound is sodium chloride, found as rock salt and in seawater. Bromine is a dense, poisonous reddish-brown liquid which easily vaporizes and turns into a gas. Compounds of bromine are less common, but seawater is a source of many of them. Iodine is a solid. It has the appearance of shiny grey crystals. Iodine compounds are also associated with the sea. They're found in seaweed. Fluorine is too dangerous for us to handle. To compare the reactivity of the other halogens, we can see how they each react with the same metal. This is iron wool. For it to react with iodine, it's placed above a few crystals in a boiling tube, in a fume cupboard. Heating the iodine turns it into a vapour. A Bunsen flame gets the reaction going. After several minutes of strong heating, only a small amount of the iron has reacted. It's become coated with reddish-brown iron iodide. Put bromine in the tube instead of iodine, and it immediately vaporizes. Again, the iron wool needs heating, but not as much. This time, there's an easily visible reaction. A mixture of unreacted bromine and brown iron bromide pours out of the tube. Bromine is more reactive than iodine. It's above iodine in the periodic table. Chlorine is above bromine. So how reactive will chlorine be? The apparatus on the left generates a stream of chlorine gas. Concentrated hydrochloric acid is slowly dripped onto potassium permanganate. This time the iron wool needs the slightest lick of a flame before a violent reaction races along. Clouds of pale yellow iron chloride quickly form. Chlorine is very reactive, but which halogen is the most reactive? halogens also react with aluminium. Chlorine reacts violently with aluminium foil. It's not long before clouds of aluminium chloride leave the tube. Bromine also has a brisk reaction with aluminium foil. Iodine and aluminium powder react once a drop of water has been added.
Alright, so there you have the halogens, and it shows you how quickly they react. Alright, there they are, the halogens, and so notice how they said that fluorine was too dangerous for them to work with because fluorine is very reactive. Chlorine is the most reactive they showed you, and bromine was a little bit less, and iodine was even less. And we're going to actually do a little bit of work with iodine in class. Okay, that brings us to the noble gases, which you also need to memorize. Group 18 are the noble gases. They have 8 valence electrons. Now remember, how many electrons do they want in their outer shell? 8, the octet. So noble gases have all they want. That makes them inert or non-reactive under most cases. I kind of think of the noble gases like snooty nobles and the aristocracy, and they don't want to hang out with all the peasants or the common folk, so they keep to themselves. So there they are, the noble gases, group 18. Now what can you tell me about these guys? Okay, now helium does not have 8 valence electrons. It only has 2 because it's in that group, it's in a period 1. So it has the 1s2 filled up. That's helium, but the rest have 8. So you could tell me 8 valence electrons because it's in column 8. It doesn't react because it already has all the electrons it needs. Same number of protons and electrons. Group 17, minus 1 because it gets 1 electron. Group 16, minus 2 because it gets 2 electrons. Group 15, normally a minus 3, but there's even more options. And then we kind of have to skip past all the rest over here to the alkali earth metals, which would be a plus 2, and the alkali metals, which would be a plus 1. All right, we'll review all of these in class a little bit, and we'll do a few activities with them. But that's the end of your notes, and I will see you soon.